Welcome back to our 7th video for Chapter 4, Effects of Electric Current. In the last video, we studied the construction of DC motors, and we know that in a DC motor, the electrical energy is converted into mechanical energy. That is, when we use a battery or a cell, the current passes through the coil creates its magnetic field, and this magnetic field is placed in the presence of another magnetic field, and therefore the coil starts rotating. So here we are in a motor, we are converting electrical energy into mechanical energy. Anything that is placed on this axle will also rotate along with the coil, right? So let us think now, what will happen if a magnet is moved quickly in quick successions, okay, in and out of the solenoid coil. Okay, so the magnet is moving in and out. Let us observe this galvanometer. Now, galvanometer is mainly used to detect traces of electric current. It also helps us to detect the direction in which the electric current is moving. So what you notice here with the galvanometer, the arrow sometimes points this way. It goes to the right, then it deflects to the left, then it comes to 0, then again points. You also notice the magnitude. It starts with 0, then it increases and then becomes 0, and then again starts increasing but in the opposite direction, right? So here what's happening is we are not using a battery at all. We're just moving the magnet in the coil, in presence of the coil, and we find electric current generated. In the second picture, we have the coil now. What will happen if we can rotate the coil, cutting through the magnetic fields? The magnet is constant, the magnet is kept steady here, and the coil is made to move, like in this picture as well. We have used a horseshoe magnet. The magnet does not move. Here the coil is made to move. So here we are using mechanical energy, and when the coil is moving, and if the circuit is completed and you use a bulb, you will find that the bulb glows. Now this is because when the magnetic field is moving in and out of the coil, or the coil is moving in and out of the magnetic field, we realize that there is a difference in the lines of magnetic field that it is cutting through. Okay, and therefore current is generated, which is called as induced current. And this law, or this particular process, is also called as electromagnetic inductions, as discovered by Michael Faraday. So these are electromagnetic inductions. Michael Faraday used this particular process of electromagnetic induction, or this property of electromagnetic induction, in order to generate electric current, and therefore the devices where electric current is generated is called as generator. Okay, so scientist Michael Faraday, he noticed that when coil moves in magnetic field, electricity gets generated. Or if the magnet moves in the coil, either way, either the magnet moves in the coil is steady, or the magnet is steady and the coil moves. We use split rings. If we want to convert DC current, we can use the split rings. If we want to generate AC currents, then we have to use the slip rings, which we will study when we study AC generators. Now, what is the statement of Faraday's law of induction? Whenever the number of magnetic lines of force passing through the coil changes, the current is induced in the coil. This is called as Faraday's law of induction, and the current induced is called as induced current. Let's know a scientist now. Michael Faraday was an experimental scientist. He was not formally educated. Teenage Michael started working in a book binding shop. While reading books, he got interested in science, and it was Sir Humphrey Davy who appointed him as a laboratory assistant in the Royal Institute of London. There he discovered the laws of electromagnetic induction and law of electrolysis. And several universities offered him honorary degrees, but Faraday refused to accept such honors. Now, Faraday's law of induction also implies that if current is switched on or off in a solenoid coil, electricity will be induced, because you're cutting through, you're increasing or decreasing the lines of magnetic field by switching on and off the coil. Also, if the current in the solenoid increases or decreases, induced current will be generated. If the coil is moved aside from front of the coil, from the solenoid, that will also induce electric current. Thus, it means whenever the number of magnetic lines of force passing through the coil changes, current is induced in the coil. This is known as Faraday's law of induction. Okay, so this is what we need to keep in mind. Either the magnet moves, the coil is steady, or the coil moves and the magnet is steady. In either case, induced current will be generated. Now, what is the difference between motors and generators? Motors use the movement of the coil to convert electrical energy into mechanical energy. So there we use battery or a cell, and that is, we are using electric energy, and electric energy passes through the coil. The coil behaves as a magnet. This coil, which is behaving like a magnet, is placed in presence of another magnet, and therefore it starts rotating, it starts moving. So we have converted electrical energy into mechanical energy. If you attach something to the axle that is moving, you have created a small motor. Okay, and if you use split rings, you have created an DC motor, and if you use slip rings, then you will create an AC motor. But in motor, we convert electrical energy into mechanical energy. On the contrary, what are we doing for generators? In generator, we are converting mechanical energy, the moving coil. Okay, if the coil is made to move, or if the magnet is made to move, that will generate electric current. So converting mechanical energy into electric current. Now, how will that coil move? That must be the question in your mind. How will it move? You are not providing it with any electricity. Okay, so you can use anything. You can use thermal power, that is the steam. Then that becomes thermal power stations. In thermal power stations, the heat, that is the you can say the steam, is used to turn the turbine. Okay, that huge handle, the huge turbine is turned. The turbine in turn is attached to the coil, and the coil rotates in magnetic field. If you use solar energy, then that becomes solar energy is generated. You are using the solar energy to move the turbine. If you use wind energy, then you're creating wind energy. Okay, that is, you are using the power of wind to turn the turbine and then generating electric current. At the hydroelectric power stations, what do you do is the moving water, the water falling from a height, is used to turn the turbine. Okay, now turbine is attached to the coil, and the coil then starts rotating. And so you're not using any electric battery or cell to move the turbines. You're using either hydro energy, or you're using wind energy, or you can use solar energy, or maybe you can use thermal energy. Okay, so that is how we create generators. In fact, we create electricity through generators. Okay, the fans that work in our homes actually use our AC current. The current that comes to our home is AC current, which we will be discussing in detail very soon. In generators now, in order to show the direction of induced current, we use the Fleming's right hand rule. So far we have studied the Fleming's left hand rule to study the direction of force, the magnetic field, and the current in case of motors. In motors you use Fleming's left hand rule. Okay, but now we use Fleming's right hand rule in order to show the direction of force. When the force is upward, you place your thumb upwards, then the index finger points the direction of the magnetic field north to south, and then the middle finger, they are all placed perpendicular, just like the Fleming's left hand rule. All three are placed perpendicular to each other. So what you find is the finger now, the middle finger is pointing inwards of the coil. So when the coil is pushed upwards, the current is moving in inwards in the coil. And when the current, when the coil is pushed downwards, then you have to invert your thumb downwards. Okay, then but all three have to be perpendicular to each other. Now you find the thumb is downward, that is the coil is being pushed downwards. The current, the magnetic field is the same with the index finger north-south, but the current now is outward in the coil. Okay, so the Fleming's right hand rule will give us all the three directions. So Fleming's right hand rule gives which direction the induced current flows. Right hand is held in such a way with thumb, index finger and middle finger mutually perpendicular to each other at right angles, just like the left hand rule. The thumb is pointed in the direction of the motion. So if the coil is moving upwards, your thumb should be moving upwards. Okay, and when the coil is pushed downwards, then your thumb should also move downwards, because that is showing the direction of force. The index finger shows the direction of the magnetic field, and the middle finger points towards the direction of electric current. Okay, when the motion of the conductor is upward, point your thumb upward. When the coil motion is downwards, then point the thumb downwards. These rules are named after British engineer John Ambrose Fleming, who invented them. Okay, now an equivalent version we have seen is also the Fleming's left hand rule, which is used for motors. Now neither the direction of motion nor the direction of magnetic field has changed. What is changed in case of generator is the direction of the induced currents. So what is the difference now between AC and DC current? When you say DC current, it's non-oscillatory current flowing in one direction in a circuit. It only goes in one direction. Okay, it has no way of going back in the opposite direction, and it is non-oscillate. That means it's not periodic. It does not oscillate high, low, like in case of DC, in case of AC current. AC current, I'll be showing you with the help of a graph very soon. Okay, just remember DC current is non-oscillatory. It does not oscillate. It can be increased or decreased or can remain stable, but it cannot oscillate between high, low, high, low, high, low. Okay, then AC current is oscillatory, changing in magnitude and direction after every equal intervals of time. The direct current can increase, can be stable, or it can also reduce, but it cannot oscillate. Alternating current can oscillate. It increases to maximum, then it reduces to zero, and then increases to maximum again, but in the opposite direction. Direct current flows in one direction throughout. Alternating current flows in a periodic manner, first in one direction, forward direction, and then reverse in the second half. Okay, so here you find the diagram for AC and DC current. Here you have used a battery. Here there is no battery. Okay, this could be a bulb or any other gadget that can be used. Okay, so here you find current in only one direction. Here you find current in this direction, and then coming back to this direction, again going back to this direction, and then coming back to this direction after every half a turn. Now if you draw a graph, you will find for every minute or every half a minute. For DC current, the current is giving you a straight line. The current is non-oscillatory. It is the same throughout. Okay, on the other hand, what is happening to AC current? It's starting from zero, becoming maximum, then becoming less, and again comes to zero, and then again it starts increasing but in the opposite direction, and then it starts decreasing till it becomes zero again, then it increases to maximum, and then it becomes zero again, then it increases to maximum but in the opposite direction, because the alternating current occurs in sinusoidal manner, okay, with time. Hence the symbol SNU is also used, okay, to show AC current. So therefore here we are showing AC current with the help of this symbol SNU. Okay, in the next video we will be studying about generators. So till then, take care, bye bye, and God bless.